Okay, so welcome to Math 389 Advanced Analysis. This is lecture 12. So what I want to do first is I want to do Zeno's bank. I'm going to do a slight modification of the standard Zeno's bank. This is inspired by one of my probability students who I was chatting with, who told me he got this from Professor McPartland in the philosophy department. How many of you have seen Zeno's bank before? Okay, so you can help correct me if I start doing things a little bit wrong, other than the ways I want to do it wrong. Okay. And so, the big theme of this class, and one of the books that I'm writing is on interchanging operations. When can you do things in different ways? And so, you want to collect as many situations as you can, where when you change things, strange things happen. And this often then says, okay, we have to put in some additional constraints. We can't just willy-nilly do this. We need some conditions. Maybe the integral of the absolute value is finite. Now we can do this. All right. At some point, maybe we should talk about the Banach-Tarski paradox. How many of you have seen that? Yeah, it's just technical stuff. I don't know if I want to lecture on it, but I'll think about it, at least mentioning this. So here's how Zeno's bank works. And this is my modification. I guess before we do Zeno's bank, is everybody familiar with the original Zeno's paradox? That you can't move because before you can move 1 unit, you have to move half a unit. And before you can move half a unit, you have to move a quarter of a unit, and et cetera, et cetera, et cetera. So there's no way to move. Well, an equivalent formulation is there's no way the tortoise catches up to the slower moving here, because before it moves 1 unit, has to move half a unit or cover half the distance, and so on and so on and so on. And so there's lots of ways to try to handle this. And there's a huge difference between the real world and maybe mathematical models of the real world. So one thing is, in the real world, can you move continuously? Seems like it. And yes, from the scale that we're looking at, it looks like it. If you are running at 10 miles per hour on a train that's going 100 miles an hour, everything in special relativity uses trains because that was the fastest method of transportation back then. It looks like you're moving at 110 miles an hour. It looks like speed is additive, but it's not. The difference is so small, we can't really notice it at the level of people running on trains. But in some theories, we can now measure these small differences, and today we can actually measure the relativistic effects. This is important for GPS satellites. Those small little bits matter. One of the best quotes I ever heard was, I think Feynman said, quantum mechanics is so accurate, it can measure the distance from downtown Los Angeles to Boston to within the thickness of a human hair. This is how many digits of accuracy you have. If it's not exactly equal, then speed is not additive. And the deviation is a function of how fast you're going. The closer you are to light speed, the more of an impact it has. So one question is, how do you handle Zeno's paradox? Is time discretized as well, that you can only move discrete amounts in space at discrete amounts in time? So here is a banking version problem of Zeno's paradox. So we will call this Zeno's bank. And you can do it in one of two ways. In one way, we do things at time 1, time 2, time 3, time 4, time 5, and we look at the limit. The other way is we do something at time 1, then time 1.5. Well, let's do time 1, 1.5, 1 3/4, 1 7/8, et cetera, et cetera, et cetera, so that in the limit, we're talking about what happens at time 2. Do you have any preference between changing my time like that to doing everything 1 unit? Okay, either is fine. All right, so either do things at times 1, 2, 3, 4, 5, and look at limit, or do at times 1, 3/2, 7/4, right? And then 15/16, and then 31/16, and look at time 2. All right, and here's how it works. We have two people, Alice and Bob. Right. This is inspired because before class, somebody said that we're doing RSA, and in RSA, the first two people are always named Alice and Bob. What?
Shelley used.
I don't want to hear this. I don't want to hear this. Sacrilegious not to use Alice and Bob. The only freedom you have is the third person is either Charlie or Eve. You have a choice of two names. What was used?
I forget the A, but the second was Ben.
Oh wait. Okay, it looks like it's paused recording. Okay. So we are talking about the Bank of Zeno. And so for the Bank of Zeno, let's see, things are being recorded. Yes. We have two people, we'll name them Alice and Bob. And at time n, capital A, Alice sends Bob her nth Alice dollar. Okay. Alice is infinitely rich, by the way. So it's good to be Alice. So at time n, she will send Bob her nth dollar. Okay. At time 2 to the n, Bob sends Alice back her nth Alice dollar and sends his nth Bob dollar. And actually, instead of 2 to the n, let's make things a little bit easier. Let's make it 10 to the n. I think 3 to the n should probably be enough. 3 to the n should be good enough. Right. So let's see what happens. So here we'll have time, Alice, Bob. At time 1, what happens? And Bob gets an Alice dollar, right? So Alice sends A1 to Bob. What happens at time 2? Sends A2 to Bob. It's good to be Bob. At time 3, what happens? So she gets A3. Bob sends back A1. And also B3. Well, actually B1, I think. It's B1. So do we agree that at time 1, Bob is +1? At time 2, Bob is +2. What about time 3? +1. All right, let's continue. So time. Yeah. So at time 4, Alice sends A4 to Bob. At time 5, Alice sends A5 to Bob. At time 6, she sends A6 to Bob. At time 7, she sends A7 to Bob. At time 8, she sends A8 to Bob. At time 9, she sends A9 to Bob. But now what does Bob do? Sends back A2 and sends over B2. And now if we look at Bob plus, it's not Bob. So Bob was +1 after 3. So now Bob is plus 2, plus 3, plus 4, plus 5, plus 6. But now we send back 2 and we gained 1. So it's going to be plus 5. So if you look at this, would you rather be Alice or Bob?
Well, Alice is infinite money, so
And Bob has infinite money. I mean, right now I'm happy to be either.
yeah.
Which do you think is better?
Depending on the
Why,
time
why
scale,
Bob?
Bob gets money more often.
Bob is getting money more often. So does it seem like it's better to be Bob? Why not? You seem to disagree. They're both infinite. But Bob is plus.
Every
Maybe you
dollar,
can create like some kind of bijection.
every dollar he gets sent back.
Ah, so here's the interesting thing. So
See how like minus and
every dollar Bob gets from Alice, he eventually gives back.
actually this is dead.
And he gives his own money. So by doing it like this, if I look at the $15th of Alice, when I hit 3 to the 15, she gets that back. Now, she's giving Bob a lot of money in the intervening time. It takes a while to go from 3 to the 14 to 3 to the 15. Bob is getting a lot of Alice money. At any moment in time, is Bob a net plus or a net minus? Bob is a net plus. What happens in the limit?
That minus everything.
In the limit, Alice has all of Bob's money. But at every moment in time, Bob was doing better.
There's no limit. I mean, they both have money. There's no limit.
But because I'm assuming they both start off with a countable infinity of dollars, right? You give me any number, and I know exactly when Alice is going to give that money to Bob, and I know exactly when Bob is going to give it back to Alice. And then once Bob gives Alice one of his dollars, he never gets it back. At any finite moment, Bob has a positive balance. In the limit, Bob has lost everything.
But why has Bob lost everything in the limit? For the limit doesn't even exist.
Well, so this is the question: is can I just take the limit? Well, but I'm saying you give me any number, and I know eventually, if the number is 17, Alice eventually at time 17 gives Bob her 17th dollar,
Right.
and at time 3 to the 17, Bob gives it back. So in the limit, there is not $1 that Alice has given Bob that he hasn't returned.
Right.
And Bob is constantly giving Alice money. So you give me any of Bob's money, 2015, and I know at 3 to the 2015, Bob gives that dollar to Alice. All of Bob's money in the limit goes to Alice. What do others think?
Well, you don't really care about the limit because your life isn't, infinite.
It's true.
How did you know?
Who cares about infinite debt if you die before it's
In the long run with that.
In the long run of a dead, yes. Let's enjoy the ride. But I can consider this as a thought experiment. And that's why the other formulation is you do things at 1, 3/2, 7/4, 15/8. Because then if you're doing it like that, you just accelerate how often you're giving things.
To the limit not existing, I kind of agree with that intuitively because it's a sequence that's strictly positive. And if we say he loses everything, then it's verging to something negative, which is.
There's a reason these are called paradoxes. This should not, something should be wrong here. So, I mean, if I look at the second formulation where I'm just increasing the frequency of exchanges. This means that I can move massive amounts of money arbitrarily quickly. If I need to transfer, that's fine. Well, actually, at any moment in time, I'm only moving at most, $2 from Bob and $1 from Alice. So the amount of money being transferred at any moment is small. But I'm assuming that these transfers happen instantaneously and that I can do them in arbitrarily small periods of time. Mathematically, I can construct such a process. And I can ask what happens. Now, again, whenever you see an infinity in mathematics, this is a warning that you must be careful. As soon as you see an infinity, you have to be careful. It is worth every now and then thinking about problems like this as to what is the foundation that we are working on. So has everybody here taken real analysis? Okay, you should have seen Dedekind cuts. This is something you see once in your life and you never see again unless you teach real analysis. That here is a rigorous way to try to construct the reals and to view these as limits. We have to be careful about what we mean by taking limits. Now here I'm taking limits with two banks that each have infinitely many items. This paradox would not exist if there was only a finite amount of money in Alice and Bob. And so the point of this is another just great example of how careful you have to be. So there's a whole slew of problems like this that are all related. And again, if people are looking for things to write up, we want to somehow exchange we want to take some kind of limit. It doesn't feel like it should be wrong to take this limit. If the limit doesn't exist, okay, fine. But I shouldn't have Bob coming out negative. At the very least, have it come out balanced. But if I just take the limit naively, at every moment in time, Bob has a positive balance. I can see, sure, in the limit it becomes 0, fine. The limit's always greater than or equal to 0, and the limit's 0. I could maybe argue he always has at least a +1, so in the limit it should be at least +1. But of course, from some point onward, it's always going to be at least a +5. From another point onward, it's going to be, if you just think about this, from some point onward, it's always going to be at least a certain plus. But in the limit, Bob has nothing. So just something fun to think about. Okay. For the next topic for today, going back to something I did in problem solving. So we might have done this in the problem solving class. We talked about differentiating an infinite sum. And we showed how it was easy to do for the geometric series. Why was it easy to do for the geometric series? Closed form for what?
For the series.
For the series, more than just a closed form for the series. There's something extremely important that we needed to do a nice way to take the derivative of the infinite sum.
Uniform convergence.
I'm sorry?
Uniform.
Well, okay, but if we use that, now we're using some real high-level analysis, which you guys don't seem to have done. But there was a cheap way that we could do it for the geometric series. And this is something special.
Just turn by turn.
Wait, but why were we allowed to do it term by term? There was something special about the geometric series, about the tail of the geometric series. It converges quickly, but you need more than just that. Because if I give you something that absolutely converges, it might converge quickly. What do you know about the tail of a geometric series? It's also a geometric series. And that's why we could differentiate term by term, because we could take the first n terms, and then what's left over is a geometric series times, say, x to the n or x to the n plus 1. Then we use the closed form expression, which you mentioned, and now we have a finite sum. So there's a closed form for the geometric series, plus the fact that the tail is a geometric series. And so what I want to kind of do is show you another way to calculate the sum of the term-by-term differentiation. And this goes back to a problem that I came up with when I was doing some math lectures during the school shutdowns of the pandemic. And so just as a preamble to make sure we're all on the same page, everybody remembers the finite geometric series formula. Everybody remembers if r is less than 1 in absolute value, we can just take the limit and get 1 over 1 minus r. All right. Has everybody here seen Star Wars? Everybody has seen Star Wars? Darth Vader, probably not going to win Father of the Year. I mean, later in the series, he does redeem himself, but he's not that forgiving. And there's a great line in Return of the Jedi where your Darth Vader goes, the Emperor is not as forgiving as I am. And given that Darth Vader is not really known as being a forgiving person, you wonder, does the Emperor kill you before you make your first mistake? Darth Vader seems to give you one mistake. An Empire Strikes Back, the Admiral comes out of hyperspace too soon, end of the Admiral. So here's an interesting question. Let's say once you make a mistake, Darth Vader kills you. No one fails Darth Vader twice because no one has the opportunity. If your probability of taking on a task is P, how many tasks until you die on average? How many of you have seen this problem in probability? It's a great problem. Can you give me some feel for what the answer should be? Lower bounds, upper bounds, anything. It's okay if there's stupid upper bounds or lower bounds. Bounded above by infinity, bounded below by 0. You can do a little bit better than 0. 1. What do you think the probability, how do you think the number of tasks you can complete before death changes as P gets closer to 1? It increases. So as P gets close to 1, it should be getting larger. What happens as P gets closer to 0?
That's only probability of failure.
Oh wait, is P the probability of failure?
Yeah.
Oh, P is the probability of failure. Okay, so as P gets closer to 1, what should happen for your probability of? Right. So you should basically be dying immediately as P gets to 1. So as P gets closer and closer to 1, then the expected number of tasks should go to 1. As P goes to 0, what should happen to the number of tasks you expect to complete? Go to infinity. So I want a function that goes to 0. So that goes to infinity as P goes to 0 and goes to 1 as P goes to 1. 1 over P. So it's not horrible to conjecture. Maybe the answer is 1 over P. And so I fix all these. Okay. So what's the probability that your first failure is on your first task? P. First failure is on the second task. Right. And so you can always see this very quickly. And so you can see it's basically going to be a geometric series. So it's a little bit annoying because different people have slightly different conventions as to how they normalize these things. But so we can calculate what's the expected value of the number of tasks you complete. And so the expected value is just n times the probability you did exactly n tasks before you died. So it's 1 times the probability the first fail is at 1, plus 2 times the probability the first fail is at 2, and so on and so on and so on. And so if we put in our values, we get that this is exactly, did I make a mistake here? Oh, the exponent fell down a little bit. The exponent should be 2. Okay. Does this look like our infinite sum from before? It looks like a geometric series that we're taking the derivative of. What are we taking the derivative with respect to? 1 minus p. So you've got to factor out the p first, and then let 1 minus p equal x. And it looks like we're taking the derivative of that infinite sum. So we showed how to calculate this by justifying the term-by-term differentiation. Does anybody know another way to calculate the value of the sum? So how would you Okay, that's fine. Can anybody give me a way to bound this sum? We know it's going to be p times something.
Down as in upper down.
Upper bound or lower bound? Can you do something that would give me a lower bound for this sum?
Let's make all the coefficients like 1.
Good. So if we make all the coefficients 1, that gives me a lower bound, and we can bound that with the geometric random variable. Can you give me an upper bound? So I've got 1, 2, instead of 3, what if I used 4? And then instead of 4, I use 8. So again, if you can't solve a problem, try to get some bounds. So if we replace the 2, 3, 4 with 1s, it's a geometric series formula where now the ratio is going to just be 1. And so that is going to be 1 over 1 minus the ratio, which is 1 minus p. What do we get? We get 1. So our lower bound is 1. It's correct. And as a lot of people would say, like most pure mathematics, completely useless. Right? We didn't need to do all of this work. And then again, I apologize that the exponents seem to be falling down. It should not have fallen down, but squared, cubed, squared, cubed. So we did too much. Could you get a better lower bound? Do we all agree that this lower bound sucks? This is a technical term.
Yeah.
Right? How could we get a better lower bound?
Say all the coefficients are 2.
Good. So keep the first one as 1 and then replace everything else with 2. So keep that second term as it was. Or you could keep the first 3 terms as they were and then change from that point onward. So you keep just a few terms in the beginning. And then the hope is, as you have a higher and higher power of p, that will do a little bit better. Oh, wow. It was not this way when I looked on my screen. Okay. So this then becomes an interesting game of trying to figure out how to fix things. These are clearly going to be squares and cubes. And then this should be 2 cubed, and then that should be 2 squared. So this is the upper bound. What do I have to be careful about? Well, you said replace everything with powers of 2. So instead of 2, 3, 4, 5, I'll have 2, 4, 8, 16. And then just use a geometric series. What do I have to be careful about?
Goes to 0.
What goes to 0?
Oh, yeah.
If each term has to be going to
Yeah.
0, so the ratio has to be what? Less than 1. So what do I need about 1 minus p if I want this to work? Less than a half. So sometimes you can get bounds only in certain ranges. If 1 minus p is less than a half, then 2 times 1 minus p is less than 1, so I can use the geometric series formula. So if 1 minus p is less than a half, which is the same as p is greater than a half, then I can use this. And so if p goes 3/4, I get an upper bound of 1.5. So, again, there's many reasons why I like this problem. I love, love, love getting upper and lower bounds, trying to get a feel for a problem. And again, if somebody's looking for a good math outreach to write up, I think this is a fun one. I've got some partial notes from a former student on this. But we now have upper and lower bounds. And then you can ask, how good are the upper and lower bounds? Well, the more terms I keep, the more accurate it's going to be. And so, here is a plot. If you look down here on the very bottom, I think that's the completely useless bound of 1. But now we can get some better bounds, and see what the truth is versus what we might get. So of course, this bound only works if the upper bound only works if p is greater than 1/2. But that's fine. What would you do for smaller p? Can you come up with a way that you might be able to handle this and still get something? So I'll leave that as something to think about. All right. So all right, so using calculus, we can show that the above sum is 1 over p. And we talked about why this is reasonable. We talked about the extreme limits. And now, here's how to do this without calculus. So I'm going to let q be 1 minus p. This is a standard probability notation. They are dependent here. They are related to each other, but let's just not keep writing 1 minus p. So my sum is p times 1 plus 2q plus 3q. I won't say the next term, and so on and so on and so on. We can write it in a very clever way. So is this justified? It converges absolutely, right? So if it converges absolutely, can I add the terms in any way I want? Why would I want to do it like this? Each is now a geometric series, and each has the same ratio. They just change where they start. And so now each one of them is 1 over q with some power of q in front of it. Interesting. So those exponents were correct, but these exponents fell down. Very, very strange. And so now we have p times pq plus pq squared. We just pull out a p. We have 1 plus q squared. Well, what does that equal?
Whenever you're using math mode.
Maybe that's it.
You're not using math mode.
Maybe that's it.
Yeah. Because other letters.
Yeah. Yeah, maybe that's it. So what's the sum on the left going to be? P times 1 over 1 minus q. And so now we get, it's p times 1 over 1 minus q times 1 over 1 minus q. But q is 1 minus p, so we get p over p squared, which is 1 over p. So here is a way to prove that this sum is 1 over p without using calculus.
We're gonna have to justify the
Well, that's the question. How much do I need to justify the regrouping? So it is always a pain to think back as to what am I allowed to use. When you become a professional mathematician, well, of course I could do all of this stuff. That's not a problem at all. But right now, what do we need to justify rearranging the sum? If the sum of the absolute values is finite, I can rearrange. Do I need calculus for that? No. I can justify all of this without, I have to use some analysis. So, it's not completely, I'm sorry?
Yeah, that's pre-calculus, right? Oh, literally pre-calculus, right? You have to know that to do.
One of my friends is a complex analyst, and he said, it never says that, calc 1, it just says it's functions of one variable. It never says a real variable. And I think he's joking, but I'm never entirely sure. if he really just wants to teach functions of a complex variable, and then just sometimes we'll just take the real part. So I think it's a much lower ask to justify that we can rearrange the sum than to justify differentiating term by term, because you have to understand what calculus is. We can actually solve this problem without using calculus. And again, this is a point that I want to emphasize for this class, that you want to have a sense of how deep is the result. What do you really need to know? When you're doing math exposition, do I have to use calculus, or can I prove it more elementarily? You know, I was doing Pi Day celebrations at the elementary school with 4th to 6th graders. I can't use calculus, but I kind of did. And just what can I do without doing all, what's the least I need to explain? And, you know, if there's some time later today, I'll show you the non-calculus calculus I did. So when you're writing things up, it's what's the minimum amount I need to know. A lot of times when people are proving things, they use the most general power, so they use the most powerful result. Why? It's the most powerful result. What is the danger of using the most recent powerful result? It could be wrong. It hasn't been checked. It hasn't been out there as long as others. So sometimes what I like to do is I like to have a free parameter and say, let's say I have a bound of the following form, you know, x to the theta. And at the end of the day, I see, so long as theta is less than 3/8, I win. Ah, the best result known is 1/6, therefore I win. If it now turns out that the 1/6 is wrong, okay, I then have to go back to the best known result before 1/6, which was 1/5, which is still less than 3/8. So I still win. And if you have a free parameter like that, that you keep throughout your whole argument, then at the end of the day, you then say, this is what I need, this is what the literature says, but I don't actually need the strongest result. I will. Okay, we seem to be having some recording issues today, but it looks like it's been fixed again, which is great. Okay. All right, now, the next thing in math is whenever you've done something, milk it. You know, now you've got a technique, see how else you can, what else you can do with it. Okay. This is similar to differentiating identities. It's a lot of work to prove an identity. Once we have it, if we can differentiate term by term, we get new identities. Can anybody tell me what movie this is? Or at least what movie franchise? James Bond. Anybody know which movie? Anybody know what game they're playing? One of my colleagues is a grandmaster of this game, and it is backgammon. I'm sorry?
So are they betting on that?
They are betting. So normally an initial game of backgammon starts off as worth, I should not have zoomed in. Well, no, it's just the next page is easier to zoom out on because it doesn't have an image. So I will zoom out on that page and then I will go back to the previous. A normal game starts off as 1. You can choose to double the value of the game. Either person can double. If you decline the double, then the person wins your wager. If you accept the double, you then get the double cube, and whoever doubled can't double again until the other person doubles. If you have a 99.5% chance of winning, should you double? Yeah, what will the other person do?
They'll probably decline.
They'll decline. It's not worth it, right? And so it protects you from that small little chance of losing. If you have a 90% chance of winning, should you double? Yeah. So then the question becomes, where do you double? And so I taught a class on the mathematics of sports a few years ago at Williams, and we wrote a paper on when to double in backgammon and related games. You know, some of this was already known, some of this was new. You can always question as to what you consider a sport. We did not consider backgammon, but so backgammon is a game where 2 people play, they roll die, and depending on what you roll, you move your pieces. in many situations, the best roll is double sixes. And so here is a string of games. So the first game, it's related to the Darth Vader problem. So since we just did this a few moments ago, we're going to extract from the Darth Vader game the following. If I have, I checked it earlier and they had all been readjusted. If you have a probability of success, oh wait, should that be failure? Oh no, okay, this has been rephrased. Okay, if the probability of failing a task is P, how many tasks until you die? It's 1 over P. If the probability of success is P, the number of tasks or tries before you first succeed is 1 over P. And this is always, how are you phrasing things? Are you doing it to first failure or first success? They're really the same. Okay. And so, why is it? All right. So we can use this to study a new game. We'll call it the sixes game. You roll a fair die until you get a 6. How many rolls do you expect until this happens? So you roll a fair die. How many rolls do you expect? 6. Everybody agree? Doesn't seem that hard. Okay. So now let's make it a little bit more interesting. Now we have 2 fair die. On each turn, you can roll 1 die or both. The goal is to have a 6 show on each. We will assume you're not an idiot. This is a 300 level class. I think that's a safe assumption. I guess since this is being recorded, this is a safe assumption in any class at Williams. I love my employer. I love my students here. Okay. Once you roll a 6 on a die, stop rolling the die. How long do you expect it to take before both die show a 6? Can you give me any upper bounds? Can you give me any lower bounds?
So at the same time, as in when you roll.
I want both die to be showing a 6.
Okay.
And on each turn, you can either roll 1 die or both die, and we will assume you are not an idiot. I think Mark Twain once said, reader, assume you're a member of Congress and assume you're an idiot, but I repeat myself. What happens once you have a 6 showing on a die? You keep it, you stop rolling it. So can you give me a lower bound for how long it will take to get 2 6s?
6. Or like
1.
Yeah.
Right. 1 is the lower bound. Upper bound, infinity. Give me a lower bound for the expected number of rolls before you get 2 6s. 6. Give me an upper bound.
36.
36. Why 36?
Reroll both every time.
Reroll both every time. So be the idiot. That might be a nice t-shirt, right? Be the idiot. Roll both die every single time and keep doing this. I don't want to win by just rolling 1 die. I want to win both die because then I can say double 6. I'm sorry? Exactly. Can you give me a better upper bound for the expected value than 36? 12. Why 12?
You first roll 6.
Right. You first roll the first die and you don't even look at the second die. So it might have been a 6, but you're ignoring it. And you keep rolling the first die until it's a 6, and then you roll the second die. Okay, that's not so bad. Then the question would become, well, what if we do this with n die? How do you think it's going to grow? So if you do it 1 die at a time, that would grow linearly with n. Do you think it's as bad as linear?
People all of them at the same time, so there's 56.
And so the question is, can you come up with a good formula? And
Each term is kind of like a binomial. The number of successes and the number of throws on the successive term depends on the number of successes.
right, but I only care if there's 1 success on the die. So if I throw n times, the number of successes on each die is a binomial, and the only time I lose if they're all tails. What's the only way I get all tails? What's the probability of that? So what's probably on one roll I get? Oh, I'm sorry, a non-6, not tails, right? What's probably I get a non-6? 5, 6. So if I roll the die n times, and if I get no sixes, for one die it would just be 5, 6 to the n. So the probability in n rolls that I have at least 1 6 is 1 minus 5, 6 to the n. That's going to go to 1 very rapidly. But now I start looking at many die. And I want to calculate what's the probability that each die has been won at least once. So I don't know why it's not letting me move the image here. Oh, maybe I could do it like this. Okay, I could cheat like that by resizing it. Do you know the word kludge? It's something that works. You don't know why it works, but it works. It's not necessarily elegant, but do you think we can use the Darth Vader theorem?
Just for the last part. So I think.
What did we do earlier today? We just did the Darth Vader theorem. Who knows Chekhov's rule for writing? This is a liberal arts college. Come on.
I don't remember exactly what it is.
If you describe a gun in scene 1, it should be fired by scene 3. You know, you only have so much space. When you're painting a picture, things matter. You know, a good writer, you know, especially for mystery, will put all the information there, but put it in such a way that you don't necessarily realize the importance of what you just saw. And again, a lot of what I'm trying to do is really talk to you about how to do good math outreach, how to write things well. You need to put things here. Do you think the Darth Vader theorem is going to be useful? Well, you know, if this is a good unified lecture, probably, although we did start today with ZenoBank, which doesn't seem to have anything going on, right? So how would all this be useful? So we talked about how many rolls, we talked about, so we will first find the probability of winning after a given number of rolls. It's easy to find the probability of winning on the first roll. So we have 2 fair die. What's the probability you win on the first roll? 1 over 36. So that's not so bad. What's the probability you win on the second roll? How would you calculate that?
There are 2 ways.
There are 2 ways. So the first way is you don't have any 6s on the first roll, and then you get 2 6s, right? And so there's 25 over 36 ways to get no 6s, and then 1 over 36. Or you get exactly 1 6, which happens 10 out of 36 times, and then you get a 6. So part of this is now, what's the best way to explain some of these calculations? I can't move it back, but I don't care. So we can start trying to write things, you know, in a tree form. You know, we start, we roll 2 6s, and then that branch is dead. We roll 1 6, and we can keep going. Is this going to be pleasant?
Especially when it's not.
So it can get worse and worse and worse, right? But, you know, we can start trying to write down what the formulas are. You can do it recursively, and we'll talk about that at this time. So there's the law of complementary probability. If the probability something happens is P, the probability it does not happen is, again, I assume most people know basic probability. It's not a prerequisite for this course, so, all right, so the probability is just 1 minus P. So we have to always be careful about double counting. This is the bane of any time you do anything in the subject, is you count something too many times. So if we want to calculate the probability of A or B, it's just A, just B, and A and B. But it's sometimes hard to calculate just A. So what we do instead is we calculate the probability of A, we calculate the probability of B, and then we subtract off the doubly counted probability of A and B. All right, so now, what is the probability we win by the nth term? It's 1 minus the probability we have not won. What's the probability we haven't won? All right, so it's no longer so easy. So what are your thoughts? So what must be true if we haven't won?
Probably with 1, 6 or 0, 6.
No. Well, okay, if you stop rolling the die once it gets a 6, it's actually technically easier to just keep rolling the die even if it's a 6. But just pretend that those rolls didn't happen and it's still showing up as a 6. So the way we don't win is the sum of the number of times we rolled a 6 on the first die is either a 0 or a 1. The sum of the number of rolls on the second die is either a 0 or 1, and they both can't be 1 together. So probably this stuff about double counting and complementary probabilities might be useful. What's the probability that the first die is, so what do we want to calculate? The probability that we haven't won. So we want to calculate the probability that the first die is never a 6. What's that probability? 5, 6 to the n. What's the probability that the second die is never a 6? 5, 6 to the n. But what do we have to subtract off? Both being 6s. So you just get 5, 6 to the n plus 5, 6 to the n minus 25, 36 to the n. That is the probability we win by the nth term. Is that the same as the probability we won on the nth term? No. So we've calculated the probability we haven't won, it's just this. So the probability we win is 1 minus that. And what is that going to go to? It's going to go to 1. We have 3 exponentials of quantities that are less than 1. They're all going to go to 0. So good. As we keep rolling more and more times, we're going to win. And so we get a really nice formula. The probability we win by the nth term is just 1 minus twice 5, 6 to the n plus 25, 36 to the n. So if we want to know what's the probability we win on the nth term, how would you calculate the probability we win on the nth term? Subtract. Right, subtract not winning by the previous. So we could actually do a lot of these and we get these closed form expressions. So here's the probability we win on the nth term. It's a bunch of geometric random variables with some rescaling. It's not a big deal. So when we were looking at that tree, we don't have to expand it all out. We can bypass all of that. And so if we put it together, the probability we win by the nth term minus probability we win, it just simplifies to the following, which is just 2 nice exponentials. And so if we want to calculate the expected value, we can do it. I've done a bunch of trials and simulations. I've written some code to do this, just made that all available. And so the Darth-Vader theorem, if the probability of success is p, then the expected number of trials until the success is 1 over p. In other words, this sum equals 1 over p. And so these have been shut down. So whenever I have a sum of this form, I know what the answer is. So if you look at what we have to do, we have basically, this should be a sub n, so annoying. A1 plus A2 plus A3, etc. And so to calculate the expected value of this is not a problem at all. We can just use the Darth-Vader theorem. We just have to figure out what should we take for p, what should we take for 1 minus p. So if you look at this, it should be clear what we should take for 1 minus p. That should just be 5, 6. So p would be 1, 6. We have 2, 6 outside. So okay, so that's 2 times p on the outside. So the answer should be twice over p, or 2 over 5, 6, so I think 12 fifths. There we go. And so similarly, we can now handle the second one, which should be should be exponents n minus 1, n minus 1, n minus 1. So what should 1 minus p be for the second? 25, 36. And again, sometimes you have to play, some little games. We don't have 25, 30 seconds outside. Not a big deal. So when the dust settles, okay, so we get 96/11, so 8.7 volts. Is that reasonable? This is a 300 level class. I want more than seems reasonable.
Less than 12.
Less than 12,
Greater than 6.
greater than 6, right?
Right in the middle.
Right in the middle. Now, you guys have done lots of different, calculations of means, right? And so if you take, the mean of your bounds, again, just as a ballpark. And again, if one of your bounds is really good and one of your bounds is really bad, mean is not a great way to do things. But so we know it should be between 6 and 12, right? If you take the arithmetic mean of 6 and 12, what do you get? You get 9. That's pretty good. What if you take the geometric mean of 6 and 12? That's 72.
Something less than that.
8 times 8 is 64. 9 times 9 is 81. So it's
Close
8
to
plus.
It's not the same.
No, they're not going to be the
They're
same.
not the same.
Now, do you know a good way to take the geometric mean of 6 and 12?
Six root.
Yeah, it's 6 times the geometric mean of 1 and 2,
Okay.
right? And square root of 2 is 1.4 approximately. So if I take 1.4 and I multiply by 6, that's 8.4. It's approximately.
You just mean the mean, so you're good.
But I'm saying, the geometric mean actually does a pretty good job. A little bit, it's actually really interesting as to which is better, the geometric mean or the arithmetic mean. Square root of 2 is a little bit more than 1.4. It's 1.414. So that makes 8.4 a little bit closer to the 8.7. But then, of course, is it really 8.7 or is it 8.72? But they're both pretty good, actually. So we were able to calculate the answer with 2 die. We talked about, is this answer reasonable? What happened if we have more die? What do you think we would get?
Go up.
It would go up. And so my question to you, if have D die, number of rolls is what? Do you have any thought about how it should depend on D?
Go up and see.
It should go up as D increases. It shouldn't be increasing faster than I think linear in D. But do we think it's going to be as bad as linear? Do we think maybe it's like square root?
But not square root. I think. So sorry, these root.
What do you think it could be? The Dth root?
Actually, never mind.
So what's a lower bound? We still have 6 as a lower bound. So 6 is going to be less than equal to the expected value, less than equal to 60. Right. So we know it's going to be.
Just take the mean and you get a pretty good answer.
Can you use what we just proved to do better?
Yeah.
How?
It's going to be a little bit lower than expected. I don't think you could be lower than 8.7.
So let's say we have D equals 4. Do these two first. How long will that take? Approximately 8.7. and then do these two again, how long will that take? So instead of 6D, we get 8.7 approximately D halves, or 4.35D. So this is a really nice concept that once you have a result, you can basically keep feeding it in. Do you think it would now help if we fed in 4.35 and broke it up into groups of 4? Would that save us anything? So now, if we looked at 1, 2, 3, 4, 5, 6, 7, 8, this would be, say, 4.35D. Oh, sorry, 4.35, sorry, right. 4.35. Right. No. So the result was 4.35 times D. So here D equals 4. So this should be 4.35 times 4. 4.35 times 4. And then that should then be 4.35 times 8. If I just use 4.35 D with D equals 8, I get 4.35 times 8. So it's really not gaining me anything if I just take the bound.
Because it's not the true value.
It's not the true value. What would gain me is if I actually analyzed the case of 4 and got a better result and then fed that in. But if I just take my bound from doing it as two separate things, and it's not going to help to just feed that back in. It's just going to keep reproducing it. So my question is, we can reduce the constant from 6 to 4.35. Right, that's not bad. And I'm sure if we do more work, we can keep decreasing it. But do we think that there's some decay?
The first, if you have D equals 1, this doesn't work.
Right, which is not unreasonable. And so this should clearly have, if we're using something like this, D is greater than or equal to 4, because we're assuming we have 4 things and we can break it up into two groups of 2. So that's a really good point to emphasize, that just because you write down a formula, you've got to be very careful. Where is this formula valid? It's not valid when D is less than 4. So my question to you to think about is, what do you think the growth rate is as a function of D? And again, the idea is you start with something simple and you try to push it. The last thing that was remarked was doing this problem by recursion. We had this, yes. Do we end at 25 or 35? Okay, yeah, okay, I thought we had another minute. So let's say, so we start here. We could roll no 6s, exactly 1 6, 2 6s, right? And let's let X be the expected number of rolls. And I'm going to call it X sub 2 with 2 die and no 6s. If I roll no 6s, from this point onward, how many rolls do I expect to need? Yep. Is expected to be X sub 2. If I roll 2 6s, how many more rolls do I expect to need before I get 2 6s? 0. And if I roll exactly 1 6, how many expected numbers? Yeah. Is X1. So I get X2. What percent of the time do I end in this branch? What's the probability I come to no 6s? there was 25 36s, right? So 25 36 of the time, it's going to be 1 plus x2. What percent of the time do I roll exactly 1/6? That's 10 36s. And then I need, that's going to just be x1. And then 1 out of 36 times, it's just 1. Oh, sorry, it's 1 plus x1. But what is x1? Is 6. So we get x2 is 25 36s, 1 plus x2, plus 10 36s times 7, plus 1 36. Well, I've got, if I subtract the 25 36 x2 from the other side, I'm going to get 11 36s. So I get 11 36s x2 is equal to 25 plus 14. I'm sorry, no, 25 plus 70, right? Plus 1 over 36. This is why you are always careful about don't simplify too soon. Both sides are over 36. There's no reason to do any simplification. So this is just going to be x2 is 70, 80, 90, 96 over 11. And hopefully, that's what we said the answer was, 96 over 11. Right? So there's more than one way to solve problems. This is a very powerful way to solve problems, is to reduce it to something that you already know. If we have more die now that we know x1 and x2, if we have 3 die, we can set up a recurrence relation. So my question to you is, can you somehow attack this and come up with a good answer? And again, I wouldn't be surprised if something like this is known, but this is how you get to research questions. Start off with something simple, start to push it. Start to look at what's the best way to approach it. A lot of times, if you know a certain method, that's what you're going to use. There are a lot of times when students come up with better ways to attack research problems than I do because I know too much. And sometimes you just instinctively go to some of the high level theorems and say, no. All we have to do is the following. If you've ever taken the Putnam or any math competition, every problem has an answer. And it's usually, it has a nice answer. Real world research life, it's not like that. But when you're doing one of these, beautifully structured problems, there's got to be a right way to look at it. So I maintain a math riddles page. For some of the problems on the page, the only way I can solve them is to be somewhat tired and make sure I'm nowhere near paper and pen. So I have to do all the calculations in my head. It's just, there's got to be a right way of looking at it. And if I'm doing a long, tedious calculation, that's the wrong way. Some of these problems, they will fall by a long, tedious calculation. One of my favorite problems, oh my God, some people have actually analyzed every single possible combination and gotten it right without making an error. It's impressive. But if you look at it the right way, it's one line. And I'll show that at some point. It's a nice way of changing perspectives. There's a lot of good stuff in this problem. We have this infinite sum that we need, and we have lots of different ways of trying to calculate what is this infinite sum. We have calculus, but it's not at the level of calculus. And when you're doing math outreach, you really want to think, what do I truly need to explain this? When you're writing a book, what do I truly need to do this? Because the more you can justify things, the less people have to take on faith, the better. Sometimes there's more than one way to prove things. Sometimes one proof generalizes better than another. Could we generalize both of these approaches? We actually had an explicit closed form expression. That might actually be better than the recursion model if you have more things. If I can write down very cleanly what's going on, because I know how to calculate these with the Darth-Vader theorem. How bad is the recursion going to be feeding in all these values? This is why it's nice to have lots of people. You can all get together and you can say, half of us will do it this way, half of us will do it that way, and we'll report back to Miller. Right. So I will stop here. I'll try to stop here. And apologies again for all the malfunctions.